In this segment, we will be studying the central limit theorem, or CLT for short. The central limit theorem deals with data that is not taken one at a time, the way data was collected in previous chapters, but is taken 2, 3, 4 at a time, and then those 2, 3, 4 pieces of data are averaged together. And we study how the distribution of the averages is. Up here, I have data that was collected from a previous quarter from my 1130 class. And I'm showing right now what the data was when one die was rolled and what the values were. And here we have one die being rolled, and so I rolled a die, and a 5 now is recorded. And so next to the 5, a tally was kept and was recorded. The die was then rolled again, and then a 4 was tallied and recorded, and so on. So my class, my on-campus class, rolled one die and recorded the different values that they had on the faces. Next, the class rolled 2 dice and recorded the average. So what we have here is the average of 1, which meant that 2 ones were recorded, happened 19 times. Going down, we'll see that the average of 3.5, meaning that either the students had a 3 and a 4, or a 4 and a 3, or let's see what else would give us 3.5. 5, 2, 2, 5, or 6, 1, 1, 6. Either they had one of those, and they recorded an average of 3.5, and that happened 72 times. Now, what's difficult to see and to read on these is to visualize what the graph is going to look like. But if you look at one die, you can see that it's about 50 to 60 times that each face showed up, with the exception of the 40 times for face 5. Rolling 2 dice and recording the average, what we have here is that the average of 1 and 6 occurred the fewest number of times, and it increases so that we can see at 3.5 and 4 we have the most. So it starts to go up, starts to go down. Then I had my students do the same thing with 5 dice and with 10 dice. Now with 5 dice and 10 dice, when they averaged the 5 dice, so they had 5 dice that they rolled, and they averaged the 5 values together and rounded to the nearest 1/2. So for example, if an average was 1.6, it was recorded as 1.5. If an average was 1.8, it was recorded at 2. And then again, they recorded the averages here, going from 1 to 6. You can see that the average of 1 happened 0 times, as did the average of 6. And it increased so that at 3 we had the most, and then it decreased. And the last one we have is for 10 dice. So for 10 dice, we had averages of 1 to 6 again, and you can see that 1 and 1.5 happened 0 times, as did 5.5 and 6. And these were averaged to the nearest 1/2. Again, so what we did then after this is a bit cumbersome, as you know, is then we calculated the sample mean and the sample proportion. So I'll move this off and now have the sample mean and the sample standard deviation, not the proportion. And the sample standard deviation and the sample mean were recorded for, here's for one die, we had an average of 3.41, a standard deviation of 1.69, and a variance of 2.85. I'll just zoom in for the others so that you can see them a little bit better. But for 2 dice, this is for 2 dice, the average was 3.55. Similar to for 1 dice, the standard deviation, though, went down a bit from 1.69 to 1.23, and the variance went down from 2.85 to 1.52. Here we have the 5 dice averaged together. For the 5 dice, again, the average was about the same as for the 1 die and the 2 dice. We had 3.59. The standard deviation and the variance went down significantly, though. It's almost half of what we have here. And then for the 10 dice, the average was 3.56, and the standard deviation and the variances for the samples went down again. So to summarize on this part, we saw that as we rolled the dice and recorded the averages, and the averages were based on how many were rolled at a time, the sample means stayed about the same, but the sample standard deviations and the sample variances decreased. Now it's a little bit hard to see this from a chart, so what I'd like to do is put up the graphs of these. If we put up the graphs, here's the graph of rolling one die. And here's one die where X was one die, and we had 1, 2, 3, 4, 5, 6. Looking across, you can see that it's rather level or flat. And this seems to be following the shape of a uniform distribution, but for discrete data. Now, if I move up the one die and show you the shape of two dice rolled together, here we have two dice, and this was the average of two dice rolled together. One thing I hope that you notice is that the labeling on the histogram now is X bar. It's no longer X because we're averaging two dice together. The other thing to notice is that it doesn't matter what the total frequency is, meaning it doesn't matter how many times you do the experiment. What we're counting is the number of dice that we're averaging together at a time. So in this case, we're averaging two dice together at a time and recording just the average. And so when we have this average of 3.5, which goes right here, it doesn't matter how many times we got the combination of 2.5 versus 4.3. What matters is that the averages. Well, the first graph had a relatively uniform shape. The second graph certainly doesn't look like a uniform shape. We may not know what it is, but it no longer has the original shape. Also, the spread is decreasing. The first graph was quite spread out. The second graph is pushed in more together. We have more of the data surrounding the middle area and less on the outside. That tells us and explains why the standard deviation is going down. Here we have averaging the 5 dice together. So this is the average of 5 dice averaged together at a time. And again, we're recording what the average is to the nearest 1/2. And again, just like with the 2 dice, the standard deviation is getting smaller. And we know that because the data is much more centered around the middle areas, 3, 3.5, 4, and much less spread out to the 1s and the 6s. And then finally, we have the 10 dice averaged together. And this is the average of the 10 dice, and these are very much not spread out, very much pressed towards the middle. And we see that we have nothing at 5.5 or 6, meaning they didn't happen, or 1.5 at 1. And so here our standard deviation is even smaller. Well, I'm going to put up what we would have expected in theory based on this chart. In theory, we would have expected for each of these to have an average of about 3.5. And you know how to get this average. For a uniform distribution, how we take the average is we add the lowest plus the highest, and we average them together. And we would have expected an average of a 3.5. And the standard deviation, we have the formula for the variance. And we can take the square root and get the standard deviation. Well, for averaging 2 dice together, we still expect to get the average at 3.5. And now you would not know how to do these if you didn't yet read Chapter 7. But after today's segment, you will have an understanding of how to get these values. But what I'd like you to see is that going across, the expected average stays the same no matter how many are averaged together. The standard deviations, though, are getting smaller, as are the variances. So let's put this all together for the central limit theorem. What the central limit theorem tells us is we take data, and it doesn't matter what the original distribution of the data is, with very few exceptions. For example, one exception might be if all the data were the same value. In that case, there would be no reason to analyze it. And so we sort of throw out that situation because it almost never comes up. Why would you want to analyze data if every value were the same? But that put aside, we take data, and it doesn't matter what the original distribution was. It could be uniform, it could be exponential, could be normal, might not have any distribution. And then instead of recording the values, we average a certain number together at a time. And the central limit theorem tells us, or the CLT, when I say CLT, that's referring to the central limit theorem. The CLT tells us that as we increase how many are averaged together at a time, the expected average stays exactly where it was to begin with, but the standard deviation will come in. We would expect the standard deviation to get smaller. And also the shape of the histogram from plotting the data tends to become bell-shaped, like the normal distribution. Now, if you think about how we get this, I tend to think about a big pastry bag of frosting, and I pour all these little x values into the pastry bag. I squeeze it up and press it, and what comes out at the bottom then is a little value of x bar. And that little value of x bar is the average of how many I average together. Then I go to the next pastry chef bag, I think that's what it's called. You put all the values for x in, you squeeze it, and out comes a value of x bar. Then when we record all these x bars, these little values, they tend to have a much smaller spread than the original data values. So let me summarize what the central limit theorem says. The central limit theorem says that we take x, we don't know, this can have almost any distribution, known or unknown. There is some mean to x. It has some mean. And it has some standard deviation. We may or may not know what the distribution is, but there's some average and there's some standard deviation and there's some variance. The distribution for x bar, then, tends to follow a normal distribution. So look here, the distribution for x may or may not have been known and may or may not have been normal, but the distribution tends to follow a normal distribution centered at the same mean that the mean for x is, but with a variance of the variance of x over n. What this tells us is that the mean for x bar, is the same as the mean for x. So we have the mean for x bar is the same as the mean for x, and the variance for x bar is equal to the variance of x divided by n. Now what this n represents is how many are being averaged together at a time. So in the case of the dice, it didn't matter how many times we did the experiment. What this represented was, were we averaging one die, and then it would be 1, or 2 dice, and then we had 2, or 5 dice, or 10. So it didn't matter whether we rolled the dice 60 times, 300 times, 74 trillion times. What mattered was how many were averaging together at a time. And then the standard deviation of x bar will be equal to the standard deviation of x, we take the square root, divided by the square root of n. And so we have our mean for x bar and our standard deviation. And if I just put these other graphs up here just for a minute, hopefully what you'll see is that that's exactly what happened. We started out with a distribution centered around 3.5, and it was relatively uniformly shaped, and we had a standard deviation that we could calculate. Then when we averaged 2 dice together, and we saw that we were still centered around 3.5, but the standard deviation got smaller. Then we averaged 5 dice together. The standard deviation got smaller again. And we sort of have start of a bell shape. In fact, I could put this one up here too for 2 dice. But for 1 die, I certainly don't have a bell shape. I would think that this would be more a uniform shape. And then the last one for 10 dice, again, the standard deviation continued to get smaller. 10 dice continued to get smaller, but we were still centered around the same value, and we would go here. Now, what I would probably see is that if I averaged more together, 20 dice or 200 dice, or this became the game of the century, and everywhere around people were averaging dice together, and we collected a lot of data, we would see an even more accurate normal shape distribution. Well, we're going to try one of the problems now. I have a problem that's in your textbook, and let me put it up here. It's in the homework part of Chapter 7, so you can follow along right here. And we have, suppose the distribution of fly balls hit to the outfield in baseball, and I gathered this information from a previous quarter from some of my De Anza baseball players. They gave me this information. So suppose the distribution of fly balls hit to the outfield is normally distributed with a mean of 250 feet and a standard deviation of 50 feet. So this is the population information. We randomly sample 49 fly balls. So we have a population that's normally distributed, centered at 250 with a standard deviation of 50. And we randomly sample 49 of these. If x is the average distance in feet for a fly ball, then the distribution for x bar, well, the distribution for x bar will be normally distributed. The mean will be the same as the mean for x. So the mean for x bar is going to be equal to the mean for x, which is equal to 250 feet. So we put that right in here. The standard deviation will be equal to the standard deviation of, the standard deviation of x bar is equal to the standard deviation of x divided by the square root of n. So we will have 50 divided by the square root of 49. And so that's what goes into here, 50 divided by the square root of 49. Now in this case, you could rewrite the square root of 49 as 7, but normally we just leave it as the square root of whatever number we're averaging together, because it won't always come out to be an integer. Next one, what is the probability that the 49 balls traveled an average of less than 240 feet? So if I want to graph this now, we're going to graph this. Okay, here's the graph. We're centered at 250. And we're now graphing x bar, no longer x. We want the average to be less than 240 feet. So we're looking for the probability that x bar is less than 240. Here's 240. And we're going to shade in this area. The first thing which I hope that you notice is that the answer must be less than 0.50, because we're shading in less than 50%. We're shading, if we were at 250 and shaded to the left, we would be at 50%. But right now we're shading less than 50%. So on our calculator, we're going to solve this the same way we solved the problems before with the Chapter 6 material, the normal distribution. The difference is that what we're going to be doing now is just changing our standard deviation. And so whatever package that you're on, computer or calculator package that you're on, we're going to go in and go into the distributions. And so the distributions on the TI-83 at least are right here. So we're going to go into the second. And we're going to go down to the normal CDF, the second one right here. We're finding the area from 0 up to 240. And the mean is 250. And here is where our difference is. At this point, instead of putting the standard deviation in as 50, we're going to put in the standard deviation as 50 divided by the square root of 49. Now, before I press the Enter key, I want to just go over again. We're looking for cumulative area. That's why the C is the one that we want. Our lower limit is 0. our upper limit is 240, the mean is 50, and what's changed is the standard deviation is now 50 divided by the square root of 49. And it tells us that this area is 0.0808. So if I go back to the graph right here, this area then is 0.0808, and that's what the probability is equal to. So the probability that the average will be less than 240 is 0.0808. Let's look at the next question. The next question says, find the 80th percentile. Okay, so the next question we have right here is, find the 80th percentile for the distribution of fly balls. So now what we're going to do is we're going to draw our graph. We're centered at 250. X bar is right here. And we're looking for the 80th percentile. So we're going to shade in starting at 0. And we're going to stop when we think we have 80% of the area shaded in. So to me, that looks like it's about 80%. So now what we're looking for is we're looking for some value, the probability of x bar, some value x bar, so that when we're at this value, that probability that we're less than that is 0.8. So I'm going to label this k right here. So that's what we're looking for. Now this is very similar to what we did in the Chapter 6 material. We'll go in and we'll go into the inverse normal. So we'll go back to distributions. And now we're going down to the third one, inverse normal. Or if you're on a computer program at home, try to go into, find something that has percentiles. That's what you'll be looking for, is percentiles. So we have 3. The inverse normal, we want the 80th percentile. Our mean is 250. And our standard deviation is 50 divided by the square root of 49. And we find that the percentile, the 80th percentile is 256.0116. 256.0116. That's what this value of k represents, 256. So the probability that x bar is less than 256.0116, that probability, I'll make this p bigger, is equal to 0.80. That's the probability. And if I look at the graph, it does look like I have 80% shaded in. One thing to keep remembering is that we have a number line down below. This is a number line. Here's 250. Anything to the right of 250 needs to be larger than 250. Anything to the left of 250 needs to be smaller than 250. So that if we were to come up with a number here and we found that we had 230 or 240, the first thing we should do is ask ourselves if that could possibly be correct, because we're on the number line. So either the picture is incorrect or the number is incorrect. All right, to summarize up now what we have for the rest of this, we have studied the central limit theorem in this segment. The central limit theorem has 2 parts to it, and the part that I've been teaching you is the part about dealing with averages. When you take values from any distribution just about, and you put them averaged together, and you're only looking at the average score. And this happens in a lot of real-life situations. For example, if I were teaching a class, students are interested in their own individual score, and I might have a class average. But then I might be interested in comparing all of the statistics class averages for a test. So I'm not interested in each individual score, but just the average for my class compared to the average for another instructor's class to another one, and would be comparing the averages. Would expect less fluctuation with the averages than individual scores. And that's what we use the central limit theorem for. We say that the average will stay the same as the population average, but the standard deviation will decrease the more that you average together. Well, in the next segment, we're going to be studying confidence intervals, which deals with how to find an interval for a parameter that you don't know. And that's the end of this segment.